Bismillahirrahmanirrahim. My name is Amir Rashid, and today we are going to start a course, Discrete Structures. The course code of this course is CSC 102. The meaning of the title of the course means what is the meaning of discrete or continuous. There are two types of data in mathematics: discrete and continuous. We have several examples of discrete and continuous data. For example, number of boys in the class, number of candies in a packet. These are examples of the discrete data. Number of boys cannot be in decimal figures. For example, we have 1 or 2 boys. We cannot have 2.5 boys. So such type of data which can only be counted is called a discrete data. On the other way, the continuous data is the type of data which we usually measure. For example, height of a person. Usually we have heights of a person's in 5 feet 8 inch or 6 feet and 4 inch. Such type of data is called continuous data. There are other examples. For example, time in a race and distance traveled by a car. These are examples of the continuous data. Now, what is the discrete mathematics, or what is discrete structures? Usually the mathematics in which we deal only the discrete kind of data is called discrete mathematics or discrete structures. There is no agreed upon definition of discrete mathematics. However, we can define discrete mathematics as: discrete mathematics is the part of mathematics devoted to the study of discrete objects or discrete structures. This is the definition given in the book of Kenneth H. Rosen in 6th edition. Another definition I have taken from the internet, Wikipedia. Discrete mathematics is the study of mathematical structures that are fundamentally discrete rather than continuous. So in discrete mathematics, we study only the mathematics in which the discrete objects or discrete data is involved. For example, sets. We'll study sets. We have 1, 2 or 3 sets. We cannot have 2.5 sets. We will study numbers, usually the integers. They are also whole numbers. We'll study relations, graph and trees, such things which are included in discrete mathematics. There are some of applications of discrete mathematics. What kind of problems we deal in discrete mathematics? For example, if we want to calculate or construct a circuit that adds 2 integers, we can design such type of circuits in discrete mathematics. And how many ways are there to choose a valid password on a computer? These are examples of discrete mathematics which we solve such type of problems in discrete mathematics. Another example is the shortest distance between two cities using transportation system is also the application of discrete mathematics. There are many applications of discrete mathematics, and most of the applications of discrete mathematics are in computer science. For example, how can we encrypt a message so that no unintended recipient can read it? How many valid internet addresses are there? And there are several such applications of discrete mathematics in computer science. In each subject or each field of computer science, discrete mathematics is of vital importance. For example, in networks we use lot of graph theory, which we will study in discrete mathematics, and to check the validity and correctness of algorithms we will also study in discrete mathematics. There are much more applications of discrete mathematics in computer science. Now, what we will study in discrete mathematics? Here is a list of topics which we will mainly study in discrete mathematics in detail. The first topic is logic, elementary number theory and methods of proof, set theory, relations, sequences and recursion, mathematical induction, counting, relation and equivalence relations, graphs and trees. What are the books which are most suitable and easily available to the students are the reference books which are given here. The first book is Discrete Mathematics and its applications with combinatorics and graph theory. 6th edition, and this book is written by Kenneth H. Rosen. The second book you can consult in discrete mathematics is Discrete Mathematics with Applications. It's 2nd edition, and this book is written by Susanna S. App. The third book is for Discrete Mathematics for Computer Scientists, 2nd edition, and its author is John Truss. These books are easily available in library or in bookstores. You can buy or borrow any edition, any latest edition of these books if you are unable to find the exact edition. Now, the first topic we'll study today is the logic. Basically, logic has been started 2003 years ago. Aristotle has started the logic by giving the propositional logic. By using propositional logic, Aristotle draw some conclusions which are based on the truthness or falsehood of statements. The next is logic of compound statements, propositional equivalences, conditional statements, logical equivalences, valid and invalid arguments, and then we will see some applications of logic in the digital logic circuits. We will design some circuits by using the properties of logic, and then we will study predicates and quantifiers, and in the last we will try to study the logic of quantified statements. Now the first topic is propositional logic. As I have told you, the propositional logic has been given by the famous philosopher, Greek philosopher Aristotle. He said that proposition or statement is a declarative sentence that is either true or false, but not the both. Now, what is the difference between a statement, proposition, or a sentence? In English, we talk about sentences. These sentences can be true, false. These sentences can be questions, orders, anything. But in logic, the proposition or a statement is an assertion. Assertion means a statement which is either true or false, but not both. So we associate a truth value to the proposition, whether the proposition is true or false. For examples, in the following sentence, we'll see that whether it is a proposition or not. Paris is the capital of France. Now this is a declarative sentence, and it gives a complete information. So this is a proposition, and we can say that this proposition or a statement is true. Now we will study some statements which are not propositions. For example, if we take a statement, can Ali come with you? Is this a declarative sentence? No, it is a question. We cannot associate a truth value with this statement because it is a question. So this sentence is not a proposition. Another example, take 2 aspirins, or go and get me a candy. Such types of propositions are or such type of sentences are not proposition, because these are imperative sentences. Take 2 aspirins, this is basically an order, not a statement. So the sentences in which someone gives order are not propositions. Another example we take here. In mathematics, we encounter such type of expressions. For example, x plus 4 is greater than 9, or x plus 5 is equal to 3. For example, x minus 3 is equal to 2, or we can say that x square minus 9 is equal to 0. Such type of expressions in mathematics are more oftenly used. So such type of expressions are also not propositions. Why? Because such type of expressions involve some variable, and we cannot associate the truth value, true or false, with these type of expressions. For example, in the in the first expression, x plus 4 is greater than 9, if we choose the value of x 10, then this becomes true. If we choose the value of x is 2, then this expression in mathematics will be false. So there is a ambiguity in such type of expressions. So we cannot say these expressions are propositions or statements. So whenever you see such type of expressions in mathematics, we can say that these expressions are not propositions. We'll see later that these expressions can be made propositions or statements by assigning a particular value to x. But for the moment, such type of expressions are not propositions. Now we take another example. He is a college student. Now in this sentence there is a confusion. Here the pronoun he is not clear, so we cannot associate the truth value. I mean, we cannot say this sentence is true or false. The truth value of this sentence depends on he. If he, for example, he is a boy and he is a college student, then this sentence becomes a statement. But if he is not a college student, then this sentence is not a statement. So there is a confusion in this statement. Therefore this sentence is not a statement. But again, such type of sentences can be proposition if the reference of he is clear here. For example, if we say Ali is 30 years old, full stop, then he is a college student. Now in this sentence the reference of he is clear. Now Ali is 30-year-old. This is a sentence. We can associate the truth value with this sentence. And now he is a college student. Now the reference of he is clear in this sentence. Therefore this sentence is a statement now. So unless the reference of the pronouns are clear in sentences, we cannot say that these type of sentences are propositions. So we conclude that the propositions are the statements or the declarative statements or sentences with which we can associate a truth value. We can say about that whether this statement is true or false. Such type of declarative sentences are called propositions. Now some notations how we denote in logic such type of statements or propositions. Usually small letters are commonly are used to denote the propositional variables, that is P, Q, R, etc., etc., and so on. And the truth value of any proposition, if it is true, then it is denoted usually by capital T or 1. And the truth value of a proposition, if it is false, it is denoted by 0 or capital F. Now I hope you understand what are the statements or propositions. Now we move to the compound propositions. Basically compound propositions as by name we can understand, we can produce new propositions from existing propositions using some logical operators or logical connectives. As in algebra, there are operators, for example minus, plus, division and multiplication. We can add, multiply or divide two numbers. Similarly, we have logical operators in logic. The most common logical operators which are used in logic are given here. The first operator is not. We can say it also negation or negation of a proposition. The second operator is and it is written as it's given on the second number. The third operator is or, and the symbol for the or is given here. The fourth operator is exclusive or, and then implication, and then biconditional. These are operators we will use in logic to produce or to construct new propositions by using some existing propositions. For example, if we take the first operator, not or negation of a principle, what is the purpose of this operator and how this operator operates on the proposition? If we already have a proposition P, if we denote a proposition with a P, which is a small letter, as I have told you, we denote the propositions by using small letters. The negation of P, denoted by this not P, and it is read as not P, and it is also denoted by this tilde P, and so in some books it is denoted by this, and in some books in logic, some books of logic, the negation operator is denoted by this sign tilde. And what is the negation of a proposition? Here it is given, it is not the case that P, where P is any proposition. The proposition not P is read as, negation of proposition is read as not P, and the truth value of this negation of P, not P, are the opposite of the truth values of P. What does it mean? It means if P is true, if the P proposition or statement, for example, I had given you the examples of proposition. For example, the Paris is the capital of France. It is a proposition and its truth value is true. Now if we write the negation of this proposition, what we see, for example, if we denote P by proposition Paris is the capital of France, we denote this proposition by P. Now what is the negation of P? It is denoted by this P. And what is the negation? We shall write it as it is not the case that P. Now P, what is P here? Paris is the capital of France. Now this is the negation of the proposition P. We can write it also in a better manner as Paris is not the capital of France. So this is the negation of the above proposition. Now another example we can take the negation, how to write the negation of P. If we take a proposition P, today is Friday. Now what is its negation? How do we write the negation of this P? As usual, if we can write not P, it is not the case that today is Friday. This is the proper or formal method of writing negation of P, but we can write more simply the negation as not P, today is not Friday. It's more simple, so we write the negations as we write in the second negation, not P, today is not Friday. Another example of the negation. So what is the negation of 6 is negative? I just suppose that 6 is negative, but it's not a correct proposition. It's a false proposition, because in mathematics 6 is not negative, 6 is positive. So the negation of this proposition we can write traditionally, it is not the case that 6 is negative, or more simply we can say 6 is non-negative. Here please take care that we cannot write 6 is positive, because the negation of negative is 0 or positive. So it's better to say here 6 is non-negative, which is the correct negation of 6 is negative. Now I hope you understand what is the negation operator and how it operates on the propositions. Now, as I have told you earlier, that truth values of a proposition along with the proposition, that is, if a proposition is true, we say that its truth value is true, and it is denoted by capital T or 1. And if a proposition is false, its truth value is 0 or capital F. Similarly, now you are watching on the screen a table, which is, this table is called truth table, and truth tables are the tables which show all possible truth values of a operator. For example, in table here will give all possible values, truth values of the negation operator. Negation operator actually is a unary operator. Unary operator means that it applies on a single statement or a single proposition. So in table, if P is a proposition, then the all possible truth values of P are true and false. In the first column we write all possible truth values of P, and in the second column we write all possible truth values of not P. The truth values of not P depends on the truth values of P, as I have told you that if proposition is true, then not P is false, and if P is false, then not P is true. So these are all the possible truth values of P and not P. So such type of tables are called truth tables. Now we go to the second operator, which is called conjunction, and in logic we say it is an AND operator. So this operator is a binary operator. We apply this operator on at least two statements or propositions. So what is the definition of this operator? Let P and Q be any two propositions, along with we can associate the truth value. The conjunction of P and Q, which is denoted by P and Q, it is read as P and Q. This is a proposition and its truth value is true. P and Q is true when P and Q both are true and false otherwise. What does it mean? That if we have two propositions P and Q, the conjunction of P and Q or P and Q is another proposition, which is a compound proposition, because it is a new proposition made of two already existing propositions. So its truth value, now all propositions, whether it is a single proposition, whether it is a compound proposition, they must have truth values. So now the conjunction of P and Q or P and Q, this proposition will be true only if P is true and Q is true. If either of P or Q is false, or you can say if one of P and Q or Q is false, then the truth value of this proposition will be false. Here is an example of the conjunction of two propositions. If we have two propositions P and Q, where P is the proposition which is today is Friday, and the second proposition is it is raining today. Now the P and Q, what is the conjunction of P and Q? It is denoted by P and Q and written as this, and today is Friday and it is raining today. So this is the conjunction of two propositions, and it is connected by a logical connective AND. So that's why it's called conjunction of two propositions, in which we add up two propositions. Now the truth value of P and Q, or P and Q, the conjunction of P and Q, depends on the truth value of the original or single propositions. If today is Friday, then P is true, and also it is raining today, then the both propositions are true, and the conjunction of P and Q is true. If today is Friday but it is not raining today, then P is true and Q is false. Then the conjunction of P and Q is false, because Q is false proposition. The all possible values of this operator is given in the truth table. Here now we have two propositions, and there are more possibilities of truth values of the conjunction operator. Now in first column in this table we write the all possible truth values of P, and then in the second column all possible truth values of Q. Actually here we have four combinations of truth values of P and Q, because we have four possibilities. If P is true, Q is true. If P is true, Q is false. The third option is if P is false and Q is true. Another option is P is false, Q is false. So now we have four possibilities of the truth values of P and Q. And the conjunction operator, the truth value of P and Q, conjunction of P and Q, depends on the truth values of P and Q. The combination of we can say the truth value of conjunction operator depends on the combination of truth values of P and Q. Now if P is true and Q is true, the conjunction operator is also true by definition, because the conjunction of P and Q is true if both proposition P and Q are true. Otherwise, if one of P and Q is false or both P and Q's are false, in these three cases the truth value of conjunction operator is false. So the conjunction operator P and Q is true only when both P and Q are true and false otherwise. Now the third operator, which is called disjunction or. The definition of, as it is a binary operator, so it uses two propositions. So here is the definition of the disjunction operator. We have two propositions P and Q, and the disjunction of P and Q is denoted by P or Q. It is read as P or Q is the proposition P or Q, and this new proposition, or you can say compound proposition, is false when both P and Q are false, and is true otherwise. As in daily life or English language, the role of OR is what? The same role of OR is here in logic. For example, the same example, if we take P, today is Friday, and Q, it is raining today. Now the disjunction operator P or Q is this: today is Friday or it is raining today. Now this statement will be true if both P and Q are true, or either P is true or Q is true. In these three cases, for example, if today is Friday and it is not raining today, then the whole statement is true, because the connective operator here is OR. And if today is not Friday and it is raining today, then again this statement is true, because there is a OR. And if today is Friday and it is raining today, then again this statement is true. So we have three possibilities in which this statement is true. The only possibility in which this statement or proposition is false is that both P and Q are false. Means if today is not Friday and also it is not raining today, then this statement is wrong. So there are four possibilities again in the truth table. If P is true and Q is true, then the disjunction operator is true. If P is true but Q is false, again the P or Q, the disjunction operator here, its truth value is true. If Q is false and P is true, again this is true, because there is a OR. The only possibility here in the disjunction operator to be false is that both P and Q are false. Then we have P or Q is false. Now we have another operator which is called exclusive OR. You experience some examples. Let's take some examples first. We have some situations in logic where the disjunction operator that doesn't give us the clear picture in the sentences or statements. For example, if we have two propositions, P, where P is Atif will pass the course CSC 102, and the Q is Atif will fail the course CSC 102. Now if we write the disjunction of these two operators, what will be the disjunction? P or Q, which will Atif will pass or fail the course CSC 102. Now we have two statements. We have disjunction, but there is a problem in this statement. Logically this statement is not correct because either Atif will pass or Atif will fail. The both possibilities cannot occur at the same time. So what we will discuss, what we will do here is we introduce another operator, which is the exclusive OR operator. And what is the definition of this operator? In this operator, actually we exclude the possibility where the both propositions are true. Here the definition of the exclusive OR is, let P and Q be two propositions. Exclusive OR of P and Q denoted by P, and this is a sign of the operator. We write it as, we write first the plus and then we encircle it. So this is the notation of exclusive OR. Now the truth values of this operator, we define it as the P exclusive OR Q is true when exactly one of P and Q is true and is false otherwise. So here we exclude the first option of the disjunction operator here, because in this situation, for example here, Atif will pass or fail the course. The first option, the first possibility in the disjunction operator will have no meaning, because at the same time Atif cannot pass or cannot fail the course. So in the disjunction operator we have excluded the first option, this. Now we can see the truth table of the operator exclusive OR. It is called XOR and it's a binary operator. And now there are again four possibilities of P and Q. Now the truth table, we can see the truth table of the XOR operator or exclusive OR operator. If P and Q are both true, then the exclusive OR of P and Q is false. This operator is defined just to exclude the situation where we don't have the both possibilities at the same time. The next, if P is true and Q is false, it is true. If P is false, Q is true, it is true. And at the last we have, if the both propositions are false, then the exclusive OR will be false. So now we take another example of the exclusive OR. For example, we have this statement, Nabil has one or two brothers. If we write this statement in the logic form, we will write it as, we suppose here we have two propositions. For example, the first proposition is P, which is defined as Nabil has one brother. And second, we define Q as Nabil has two brothers. Then what is the exclusive OR? P exclusive OR Q is Nabil has one or two brothers. Here in the statement of this proposition, we cannot identify whether we have to use exclusive or the simple or, which is called disjunction. This is we or this is you who will decide. We will use here exclusive or the simple or disjunction. So here, as we can see that the both possibilities P and Q, the both propositions P and Q cannot be true at the same time, because either Nabil has one brother or two brothers. He cannot have one brother and two brothers at the same time. So in such situations we will use exclusive or, which will give us the truth value, the correct, we can say the correct truth value of the proposition. If we, how to distinguish or how to differentiate between the exclusive or the simple disjunction. To register for BCS, you must have passed the qualifying exam or be listed as a math major. What does it mean? To get an admission or to get the registration in BCS, you have to pass the entry test, which is qualifying exam, or you must have mathematics in, you can say, FSC. So if you have both possibilities, if you have passed the qualifying exam and also you have maths in FSC, both possibilities are possible here. So we can use here disjunction, because these two possibilities to get an admission or to get registered for the BCS, if you are qualifying for both possibilities, if you have math major, if you have mathematics in FSC and you have passed the entry test, you can even get the admission in BCS. And if you have only passed the qualifying exam, entry test, even then you can take the admission or you can register for BCS. So here the or will be used as simple disjunction, or we can say that or is inclusive here. Now we will see how we translate some English sentences or statements into the logical form. For example, you are watching a statement here on the screen: I did not buy a lottery ticket this week, or I bought a lottery ticket and won the $1 million on Friday. Now this is a composite statement, and how can we write it in logic form? To translate it in logical form, we suppose the propositions here. We say here, let P and Q be two propositions, and we investigate that in the given statement there are two things. The first, if I buy a lottery ticket, and the second is I won the $1 million on Friday. So there are two things here in this statement. So we suppose here P to be a proposition which states that I bought a lottery ticket this week, and the second statement which is used in the given composite statement is I won the $1 million on Friday. Now if we see that in the given statement we have the first thing, I did not buy a lottery ticket this week. This is basically the negation of P, because P is I bought a lottery ticket this week, and the first statement in the given composite statement is I did not buy a lottery ticket. Now after that there is a connective between these two statements. This is or. This is basically the or operator which is used here to connect these two statements. Or I bought a lottery ticket, this is the same statement which is given as P, which is the P. There is another connective here, and is used in this statement, and then we have another statement, won the $1 million on Friday. So how we translate this statement or composite statement into logical forms? If we suppose P, I bought a lottery ticket this week, and the second is Q, I won the $1 million on Friday. So in logical form, we will write the given compound statement as, here we have not P, which expresses the first statement, I did not buy a lottery ticket this week, or here we have the logical connective or, and then I bought a lottery ticket and won $1 million on Friday. So here, if you remember, I have written logical connectives in this order. First I have written the not operator, then I have written and operator, then I have written or operator, then I have written exclusive or, then I have written implication, and then I have written biconditional. These two operators we will discuss in the next lecture, and these four operators, actually these are three, and these two operators or have the same significance here. So this is the order of preference of the operators. First we will give the preference to not operator, as in algebra of plus, minus, division and multiplication there is a preference. So what is the most, if we have plus or minus in an expression, for example 2 plus 3 multiplied by 4. So in algebra, multiplication has preference over the addition. So first we multiply 3 and 4 and then we add 2. Similarly in logic we have preference to the logical operators. First we give the preference to the not operator, and then and then or, and then exclusive or, they have same preference order, and then implication, and then biconditional. These two operators, as I have told you, will be discussed in the next lectures. So this is the order of preference of the operators. Not P is a unary operator. It is applied to the single proposition. We can write it as not P. So we give the preference to the first preference to the not operator, and then or, and then we have P and Q. After not operator we have preference on and operator. So first we take here P and Q, and then we take the or. So that's why this expression is written as not P or P and Q. So this is how we can write the given compound statement in English. We can transform it into the logical form as by considering the preference to the logical operators. For example, if we and similarly we can translate or transform the logical form into the simple English statement. For example, if we have the same P and Q, and we have not P, we have to write not P and or not P and Q, not P and Q. How to write this logical expression into the English form? Here we have not P and Q. What is P? P is I bought a lottery ticket this week, and Q, what is Q? I won the $1 million on Friday. So not P and Q. How do we write this logical expression into simple English? I did not buy a lottery ticket this week and I, here we write small I won the $1 million on Friday. Actually this is not possible, but it's just to explain you how we write any logical expression into simple English by using the logical connectives. Another example, if you take this not P and not Q, what will be the simple statement corresponding to this logical expression? It will be I didn't buy a lottery ticket this week and I didn't win the $1 million on Friday. So this is the corresponding English statement of this logical expression. Similarly, we can write, there are many possibilities. If we have P and not Q, or not P and not Q. So what is the corresponding English statement of this logical expression? We have two parentheses here. The preference is given to the AND operator, and after the first of all the preference is given to the NOT operator here, we can say here, and then the preference is given to the AND operator and then OR operator. So we shall write two statements and then we will connect them by the logical connective OR. What is the meaning of first statement, this first expression? I bought a lottery ticket and I do not win $1 million on Friday. And the second statement, what is the second statement? I didn't buy lottery ticket and I do not win $1 million on Friday. Now how we will translate the whole logical expression into the simple English statement. The first expression, this expression, will be written as I bought a lottery ticket and I do not win $1 million on Friday. The second expression will be written as I didn't buy the lottery ticket and I do not win $1 million. Now we connect these two statements, I bought a lottery ticket and I do not win $1 million on Friday, or I didn't buy a lottery ticket and I do not win $1 million. So this will be the corresponding English translation of the given logical expression. Now I hope you have understand how we translate a logical expression to English and an English expression into a logic. So one thing here is to remember that please consider the preference of the operators not, and, or, and exclusive or. Now I summarize what we have studied today, and then we will finish the lecture. First of all, I have given the introduction to the course. What does mean the discrete mathematics or discrete structures? And then I have told you some recommended books which you can buy or borrow from your library to consult. And then we have started logic, and in logic we have studied the first two topics which were mentioned in that slide. We have studied today the propositional logic and logical connectives, truth tables, compound propositions. What are the compound propositions? These are basically made up of already existing propositions. And then I have given you the brief overview of how to translate or transform English statements into logical form and the logical statements into simple English sentences. So I hope you have understand everything, and we will discuss in the next lecture, inshallah, the conditional statements and the logical equivalences. Thank you very much. Allah Hafiz.